I'm pleased to welcome Dee Long to the podcast. Dee is a professor in hydrology and remote sensing at the Department of Hydraulic Engineering at Tsinghua University in Beijing. And prior to this position, Dee was a postdoc in our group at the University of Texas from 2011 to 2014. And he did his PhD at Texas A&M prior to that. So thank you so much, Dee, for joining me today.
It's my great pleasure, Beijing.
Today, I think we're going to talk about Dee and his team have worked on many different research topics. And today, I think we're going to talk a little bit about the drought work he did at the University of Texas, because he was here during the 2011 drought, very extreme drought in Texas. And then after that, we would like to talk about his work on the Tibetan Plateau Asian water tower, and then his research on changes in water storage in the North China Plain as a result of the south to north water diversions. And then Dee has used a variety of different tools and artificial intelligence and machine learning then to conduct the research, and talk a little bit about that also. So let's first start about your work when you were here at the Bureau of Economic Geology at the University of Texas. You were a postdoc here after completing your PhD at A&M. And Texas was experiencing one of the worst one-year droughts on record in 2011. And you applied the GRACE satellite data to estimate the water storage depletion as a result of that drought. The GRACE satellites are great because they provide total water storage. But one of the aspects also that you did was try to figure out what was contributing to the storage losses, whether it was reservoir storage, soil moisture, or groundwater. Maybe you can describe that work a little bit, Dee.
Okay. So that period really shaped how I think about the droughts and the water systems. When I was a PhD graduate at Texas A&M and a postdoc at UT Austin, Texas experienced the most extreme one-year drought on record in 2011. Rainfall dropped to about 40% of the long-term mean, and the impacts were enormous. Agriculture alone suffered around 7.5 billion US dollars in losses, affecting both crops and livestock across the state. And what made this drought particularly interesting scientifically was that it wasn't just a surface phenomenon. This was one of the first events where we could really use GRACE satellites to look at total water storage TWS, meaning surface water, soil moisture, and groundwater together, rather than trying to infer impacts component by component. Using GRACE data from CSR and GIS centers, we found that during the peak of the drought, Texas lost about 62 cubic kilometers of total water storage, with uncertainty of roughly about 18 cubic kilometers. To put that in perspective, that's about 50 million acre-feet, or nearly 3 times Texas' current annual water use, which is on the order of 15 million acre-feet. Well, from a meteorological perspective, the drought was very clear as well. The Palmer Drought Severity Index dropped below -2 in February 2011, and stayed there until September 2012, with an extreme minimum close to -8 in late 2011. And that helped us define the core drought period and connect atmospheric forcing to hydrological response. And a key question we are trying to address, where did all that water loss come from? Surface reservoirs did decline, but surprisingly, they explained only a small fraction of the TWS signal. Using in situ reservoir data, we estimated about 7.6 cubic kilometers of reservoir storage loss, which is only about 12% of the total Greece observed depletion. So then we look at soil moisture. We use the multiple land surface models from GL- and NL-, and although individual models varied quite a bit, they all showed a strong depletion. In fact, Greece TWS anomalies were very highly correlated with modeled soil moisture anomalies, with correlations between about 0.86 and 0.95, suggesting soil moisture play a dominant role. And in terms of groundwater, it is another important piece of information based on groundwater pumping statistics from the Texas Water Development Board. Groundwater use in 2011 was around 12 to 13 cubic kilometers, or roughly 10 million acre-feet. And in regions like the High Plains Aquifer, we estimated groundwater storage losses of around 5 cubic kilometers. So overall, groundwater likely accounted for about 8 to 16% of the TWS decline during the drought. So putting all of this together, our synthesis suggested that soil moisture depletion accounted for roughly 70 to 80% of the TWS loss, with groundwater and surface reservoirs contributing smaller but still important shares.
Right. Yeah.
Yes.
So that was a really nice synthesis. And when we experience droughts, we're always wondering what the impacts of the droughts are. And you mentioned, the huge economic losses and during that drought. And I don't know if you remember Dee, but
Yeah.
when you went out that summer, it was like going into a convection oven. It was so hot
Yeah.
and windy
Yeah. Still
but
vivid. Yeah.
yeah, so I mean, it's difficult to disaggregate the gray satellite data into the components, and we're fortunate at the University of Texas to have the Center for Space Research (CSR), who are one
Yes.
of the main groups that provide the gray satellite data globally, and then. The reservoir storage, the Water Development Board has a pretty good handle on that, and they monitor the water storage in the reservoir. So that's a pretty good number. And then also they estimate how much groundwater water is used in the state. And so you can estimate, even if you assume that there was no recharge and that all that groundwater was a net loss in storage, is still a small fraction of the total water storage depletion. So that was about 50 million acre feet, and Texas uses about 13 to 15 million acre feet a year. So even if you assume there was no recharge, that still doesn't account for all the total water storage loss. So a lot of it has to be in soil moisture, or it could be some shallow groundwater also.
Yeah, you are right. Yeah.
So with that big depletion in soil moisture, it sort of explains why it takes so long then to recover from a drought. So 2011 was the most extreme part of the drought, but rainfall after that maybe was close to normal conditions. But you have that huge soil moisture deficit that you have built up that you have to overcome before you can get runoff into the reservoirs. So it wasn't until 2015 when we had the highest rainfall on record in the state that we really ended that drought. So the drought, there was some recovery in 2012, and Nell and Fernando at the Water Development Board and Rong Fu looked at the impact of North Atlantic oscillation on some recovery at that time. But then really the drought persisted until 2015 when we had a lot of flooding, Wimberley floods in May and other floods. So 2015 was a very wet year, and you almost need a flood to end a drought, particularly one that has built up all that depletion.
Yes.
And so you've been looking at the U.S. Drought Monitor is a great record of provides a great record of droughts, and so we've been seeing those droughts, more droughts in Texas since then. Um, so I guess you have worked on droughts a lot, and your work during your PhD was looking at evapotranspiration and looking at all of
Yeah.
these different products. Um, so, what do you think of the more recent droughts in I guess we can look at those now with gray satellite data. We're developing a dashboard then to provide the GRACE data. And I guess one of the advantages of GRACE, it can give us a statewide picture of water storage
Yeah.
because it's a coarse resolution, and so you can look at the large scale.
Yeah. So I think Greece fundamentally changed how we monitor droughts. Instead of arguing about uncertainties in soil moisture models or sparse groundwater observations, Greece gave us a direct integrated measure of how much water the entire state was losing. That's incredibly powerful for drought assessment and water resources management, especially in a place like Texas, where water is managed across multiple sectors and jurisdictions. So, uh, so this work feels even more relevant today. I think Texas has since experienced the 2021 winter freeze, followed by severe droughts in 2022 and 2023, with cascading impacts on agricultural ecosystems. And Greece and now Greece follow on gives us a way to consistently track these compound extremes and understand how the system responds over time. Yeah.
And I guess also the important aspect with that water storage is how much water you need to recover from these long-term droughts, and so you get an
Yeah.
idea then from that. And there is, I mean, in your paper on the 2011 drought, you did show that the soil moisture storage, there were huge variations in the soil moisture storage from the models. But we look at a lot of different components and try to estimate the uncertainty. But it showed that we needed a lot of water to overcome that drought. And, another colleague, Mike Dettinger, wrote a paper called something like Drought Busting Floods, and it was talking
Oh,
about the atmospheric rivers in the Western US and
yeah.
how they oftentimes
Very
bust
interesting.
long-term droughts in California and other places. Um, so you went back to China in 2014, and you're at Tsinghua University. And I was listening to a book recently by Dan Wang called Breakneck, and
Oh,
comparing China and the US, and indicating that many of the politicians in China have an engineering background. And in contrast to the US, where most politicians have a legal background or went to law school. And I remember when I visited your university, there were photos of past presidents that went through your department and stuff. So maybe you can describe that a little bit, Dee.
okay. So I'm really grateful for your support over the years, Bridget, first. So including during my time at UT Austin. Returning to China was a big decision for me, but in many ways, it felt like a natural step. What you mentioned from Backneck really resonates with my experience. Engineering and science have a very special status in China, historically and culturally. Many national leaders have engineering backgrounds, and Tsinghua University in particular has long been associated with training engineers who later take on leadership roles. And President Xi is also a Tsinghua graduate. And if you walk through our department buildings, you will still see photos of former presidents and leaders in various sectors who studied or taught here. So, at a more practical level, this emphasis translates into strong and sustained investment in education and research. Most graduate students in China have their tuition largely covered by the government, which removes the financial burden and allows students to focus on learning and research. As a faculty, we also play a role in supporting students directly. This is quite similar to the US, I think. In my case, much of my student funding comes from competitive national grants, especially from the National Natural Science Foundation of China, as well as programs supported by the Ministry of Science and Technology. These funds allow us to support PhD students, postdocs, and long-term research that might take many years to mature. And also, beyond the national funding, there are also many additional sources. Some of my colleagues collaborate closely with industry, particularly in areas like infrastructure and AI. In addition, local and municipal governments invest heavily in research, especially in innovation-focused cities like Shenzhen, where research finding is often closely linked to real-world applications and rapid technology transfer. So, what I find especially exciting is that this engineering-driven culture encourages problem-oriented science. There's a strong expectation that research should eventually inform decision making, whether it's water security, climate adaptation, or infrastructure safety. So that mindset has strongly shaped how I approach my work since returning to China. So in many ways, my past reflects a broader system, strong training in China and abroad, combined with a domestic environment that values engineering, supports students, and invests heavily in long-term scientific capacity.
Right.
Yes,
Yeah. So it's great that you are doing so well at Tsinghua University. That's
thank
one
you.
of the premier universities in China. And I guess the current chairman, Xi, was a graduate from Tsinghua University.
Yeah,
So
for
that's
chemical engineering. Yes.
yeah, that's a pretty interesting. And the fact that the government supports the students' fees and that frees you up then that you don't have to try to get grant funding then to cover their tuition and all of that sort of thing. So it's a big help. So you have been working in a variety of different topics since you returned to China, Dee, and one of the first ones I'd like to discuss with you is the Tibetan Plateau and its role as the Asian water tower. Um, and providing the headwaters for many of the major rivers in China and surrounding countries, and then also providing water for with the electricity, energy production, but also irrigation downstream, supporting about 1 billion people downstream. So maybe you can describe for us a little bit the geomorphology, the physiology, the climate, and of the Tibetan Plateau, and then as your research findings on the role of the Tibetan Plateau in the bigger water system surrounding it.
Okay, so thank you, Bridget. The Tibetan Plateau really is one of the most fascinating and important regions I've ever worked on, both scientifically and personally. So to start with a sense of scale, the Tibetan Plateau is enormous. It covers roughly 3 million square kilometers, about the size of the Mississippi River Basin in the US. So the Mississippi River Basin is around 3.22 million square kilometers and has an average elevation of over 4,000 meters above sea level. So because of the extreme elevation, it's often called the third pole of the Earth. And hydrologically, the plateau is incredibly diverse. In the central Tibetan Plateau, many basins are endorheic, meaning they are internally draining. Water flows into lakes but doesn't reach the ocean. This is why you see such a dense concentration of lakes there, many of them large, remote, and minimally affected by human activity. And in contrast, along the margin of the plateau, the basins are egorrheic and form the headwaters of some of the Asia's large rivers. So from west to south to east, these include the Indus, Ganges, Brahmaputra, Nusari, Lancang, Mekong, Yangtze, and Yellow rivers. So together, these rivers supply water to more than 1 billion people downstream, making the plateau critical for water security across much of Asia. And the plateau is also extraordinary in terms of cryosphere and surface water. There are more than 77,000 glaciers on the Tibetan Plateau itself, covering about 83,000 square kilometers. And lakes are just as remarkable. The Tibetan Plateau is one of the most densely distributed lake regions on Earth, with around 1,400 lakes greater than 1 square kilometers. And these lakes occupy about 50,000 square kilometers, representing about 60% of China's total lake area. And many of these lakes have been expanding rapidly in recent 3 decades, largely driven by changes in precipitation and glacial melt. And in terms of climate, it plays a central role in shaping all of this. The plateau acts as a massive elevated barrier in the atmosphere. And moist air actually are forced upward by the terrain, cool rapidly, and release precipitation, a process known as the orographic effect. And what makes the Tibetan Plateau unique is that it's not just a mountain range, but a vast elevated landmass. And precipitation over the plateau is primarily controlled by 2 major systems. The South Asian summer monsoon brings moisture from the Indian Ocean. And meanwhile, the mid-latitude westerlies transport moisture from regions like the Mediterranean and the Iranian Plateau, dominating precipitation over the western and the northern plateau. And from a scientific perspective, the plateau is especially valuable because it is highly sensitive to climate change, yet relatively free from direct human disturbance, especially in the lake-rich interior. This means that changes in various variables like lake area and lake water storage provide a very clean signal of how the regional hydrological system is responding to climate change. Well, so we often think of the plateau as a natural lab. By combining satellite remote sensing, hydrological modeling, and now AI-based data fusion, we're able to track how glaciers, snow, lakes, and rivers are evolving, and what that means not only for the plateau itself, but for downstream regions that depend on it. So our research primarily relies on using a multi-source satellite remote sensing, including GRACE, including satellite odometry and optical remote sensing images to track changes in glaciers, lakes, and we incorporate this sort of information into hydrological modeling to understand changes in hydrological processes, including snow melt, glacial melt, and rainfall runoff processes.
Right.
Yes.
Yeah. It plays a huge role in the hydrology then of Asia. And as you mentioned, the third pole, and
Yeah.
about so much of it about 4 kilometers in elevation. and such a large area. So it would be very difficult to evaluate the hydrology from ground-based
Yeah.
approaches. So it shows the value of remote sensing then to try to understand how the system is evolving. Um, and very interesting work you did on looking at the lake water storage and its response to climate. And you mentioned, I guess, two of the main drivers of climate there, the westerlies, which means water coming from the west, and then also the South Asian monsoon system from the Indian Ocean.
Yes.
Um, and the role of orographic precipitation then supplying water to downstream users. So your work in the lake water storage, you were covering the period from about 2000 to 2017
Yeah.
and did a detailed analysis of water levels and storage changes in the lake using GRACE and altimetry data. Um, and focusing, I guess, on about 50 very large lakes, greater than
Yeah.
100 square kilometers, and talking about expanding water storage in these lakes over that time period. And some of the plots in the paper showed, 5 to 10 meter increases in lake level height, and then also there are concerns about potential glacial lake outbursts like Lake Kusai and Lake Salt and the potential impact on downstream populations. So maybe you can describe the results of that work a little bit, Dee.
Okay, thank you, Bridget. We actually conducted a detailed analysis of lake water levels, the surface extent, and storage changes between 2000 and 2017, focusing on large lakes where satellite signals are most reliable. So in total, we analyzed about 50 lakes larger than 100 square kilometers. And what we found was quite striking. The majority of the lakes showed persistent expansion, both in surface area and in water storage, over this 17-year period. In terms of water levels, a typical increase was on the order of 5 to 10 meters, which is very large when you think about the lake systems at this scale. Well, there are also these are not short-term fluctuations. They represent a sustained accumulation of water over nearly 2 decades. And when we translate those level increases into storage, the signal becomes even clearer. Many lakes gained substantial volumes of water, driven primarily by increased precipitation and enhanced glacial melt under a warming climate. Because these lakes are most located in the rig basins, the water essentially has nowhere to go. It accumulates in the lake system and evaporates back to the air. And at the same time, these changes raise important risk considerations, particularly related to glacial lake outbursts, floods, or growth. And this is something I have been experiencing very personally. In spring 2023, I joined a field expedition to the remote source region of the Yangtze River. During that trip, my former student, Dr. Peng Fei Han, who is now associate professor at Dalian University of Technology, and the two other team members were traveling in the same vehicle when it accidentally slid into the river. They were trapped in the water for nearly an hour before being rescued by others. So fortunately, everyone survived, but the incident really highlighted how remote, harsh, and dangerous these environments can be. So access is extremely limited. Weather changes rapidly, and even basic field work carries significant risk. This experience reinforced for me why we can't rely solely on in situ observations in regions like the Tibetan Plateau. And this is where remote sensing becomes indispensable. So satellite altimetry, optical imagery, and SAR allow us to continuously monitor lake levels, surface expansion, and sudden changes, even in places that are nearly impossible to reach safely. Well, so in a sense, Tibetan Plateau lakes serve two roles at once. They are first indicators of climate-driven hydrological changes, and they also are potential sources of hazards. So understanding both aspects, long-term storage trends and short-term instability is critical for risk assessment and downstream water management. Yes.
Yeah, that really highlights
Yeah.
how difficult it is to do field studies
Yeah.
in those regions. I remember going visiting glaciers in northwest China, and people warning us because we drove up to the glacier, and they said you have to walk very slowly because the oxygen levels are so low. And everything. I was with
Yeah.
an Australian colleague, and she was much younger than I was, and she ran out there, and the next minute she was keeling over because there wasn't enough oxygen. So but it's great that we have remote sensing data. So Grace says water storage data and also synthetic aperture radar for altimetry data. And you have done that type of analysis for all of the reservoirs globally using altimetry data. So very helpful in understanding the system. And so you mentioned, this is internally draining system, so it's not impacting downstream except potentially glacial outbursts. But if it's sourced from glacier melting, then this expansion, how long before the glaciers will be potentially completely melted, and then that source will go away, and maybe you won't have continued expansion of the lakes forever.
Yes. So the lake will be so the storage and the water level of the lakes will be dependent on a number of factors, including temperature and also uh, the evaporation of the lake's water storage. If the temperature continue to rise, I think evaporation from the lakes will also increase. So the lakes, even though they are currently expanding, they will not, such kind of expansion may not be persistent for decades ahead. Yeah.
Right, right. And so if the source is glacial melt, then that could be a transient pulse over decades.
Yeah.
I can know the river flows in northwest China, but they were sourced from glacial melting. There was a high river flows in response to the glacier melting, but that won't last forever. So important to
Yeah.
consider these factors when you're thinking about infrastructure and water resources management. So, Dee, one of the aspects of your research that I really appreciate is how thorough you and comprehensive you do the analysis, and you use a variety of different sources, and you approach the problem, from the top down, for example, in the Tibetan Plateau with the satellite data, and then also from the bottom up look, and then you combine and fuse all the satellite data, and then use models and AI to better understand the system. So I guess your work at the plateau, you showing that total water storage increased about 10 cubic kilometers per year. And so for the US listeners, 1 million acre feet is about 1.2 cubic kilometers. So the units are fairly similar. And that's over the entire plateau. And in the indirect region, then the internally drained region, about 5.5 cubic kilometers. But decreasing trends in the exorate basins, about minus 16 cubic kilometers. Maybe you can describe the exorate basins and their role then and impact on downstream river flows.
Okay, so yes, Bridget, at the scale of the entire Tibetan Plateau, total water storage showed a net decline of about 10 cubic kilometers per year, as you just mentioned. But this overall number masks strongly contrasting regional behaviors. So when we separated the plateau into endorheic basins and egorheic basins that feed major rivers, the contrast was striking. So in the endorheic regions, mainly across the central and the northern Tibetan Plateau, we observed a significant increase in water storage on the order of 5 to 6 cubic kilometer per year. So this increase was driven primarily by widespread lake expansion, as we just discussed, which alone contributed nearly 5.8 cubic kilometers per year. So combined with localized glacial mass gains in regions such as the Karakoram and the Western Kunlun Mountains. And in contrast, the egorheic basins, especially those draining south and west, including the Indus and Ganges and the Brahmaputra headwaters, experienced substantial water storage losses around minus 16 cubic kilometers per year. So these losses were dominated by negative glacier mass balance associated with regional warming and changes in precipitation phase, where snowfall increasingly turns into rainfall. Glaciers in regions such as the Hindu Kush Himalaya and Niton Tangala mountains have been retreating rapidly, contributing roughly 10 cubic kilometers per year to water storage decline. So what's particularly important is that these spatial patterns align well with large-scale atmospheric circulation changes. So over the recent decades, South Asian monsoon intensity has weakened, but mid-latitude westerlies have strengthened, and this shift helps explain why southern monsoon-influenced basins are losing water, while northern and interior basins influenced by westerlies are, at least for now, gaining water. And so, in terms of the implications, those contrasting trends matter greatly. Changes in total water storage directly affect water availability, particularly meltwater, that supports irrigation and ecosystems downstream. And at the same time, they influence natural hazard risks such as glacial collapse and glacial lake outburst floods. So these processes can amplify compound risks and hydropolitical tensions in densely populated downstream regions that depend on water originating from the plateau. So taken together, this study highlights how the Asian watchtower is not responding uniformly to climate change. Instead, it's fragmenting into regions of gain and loss, and understanding that heterogeneity is essential for both science and water management. Thank you.
Right. And I think, oftentimes we just want a simple answer, D. We just, is it
Okay.
is it increasing? Is it decreasing? And are we in trouble or whatever? But what your studies highlight is the variability in what's happening throughout the Tibetan Plateau. And that's very important to understand. So it's not all decreasing. So it's increasing in the north and decreasing in the south, and then understanding what's causing those increases and decreases. Precip increase, glacier melting, and the atmospheric circulation pattern. So your work really links all of those things together. And if we want to manage things in the future, we need to understand the processes that are operating and have been operating in the past to develop appropriate water management solutions. So kudos to you and your team for doing very detailed analysis and looking at and not just coming with a simple answer. So, one of the things with satellite data is that many people think that we didn't know anything or do anything before we had satellites. And so that gets a bit frustrating, I think, for people who have been working a long time in hydrology. But I really appreciated the work you did on reconstructing stream flow over past centuries using tree ring data and also proxies for the drought, PDSI, and things like that. So maybe you can describe that a little bit for us, those long-term reconstructions of stream flow over over past centuries, Dee, and what you learned from that.
Okay, thank you, Bridget. Because instrumental streamflow records on the Tibetan Plateau are very short, mostly since the 1960s, they don't capture the full range of natural variability. So to address this, we reconstructed annual stream flow back to around 1200 CE using tree ring-based PDSI data. Technically, we were using conical correlation analysis combined with log linear regression. We were able to explain about 64 to 70% of the variance in observed stream flow at 5 key headwater stations, including the Yellow, Yangtze, Lancang, Mekong, Nusarin, and Brahmaputra rivers. So what we find is that the past 800 years include many wet and dry periods that exceed the fifth and 19.5 percentile range of the instrumental record. In particular, for gauge stations in the northern Tibetan Plateau, we identify several extremes and prolonged drought episodes that are not captured by modern observations. In other words, what we often think of as a stream today is not unprecedented when viewed over a longer time scale, but the context matters. And one notable example from this study occurs in the mid 1900s, corresponding to the Baroque period. So when we contracted the stream flow in northern rivers reaches exceptionally low levels and persists for a couple of years, these extreme drought conditions coincide with well-documented historical mega droughts in China and are widely recognized as one of the major natural stressors contributing to the collapse of the Ming Dynasty through impacts on agricultural, food security, and social stability. And a particular striking result is the strong north-south contrast with a dividing line around 32 to 33 degree in the north. North of this line, the Yellow, Yangtze, and the Lancang headwaters conditions tend to be drier when the south is wetter, and vice versa. For example, the Brahmaputra headwaters were generally wetter in earlier centuries, while many northern rivers were drier. This opposing behavior persists across about 10 major wet-dry cycles. And in terms of drivers, ENSO is dominant at interannual timescales, especially 3 to 8 years, while PDO, NAO, and the Indian Ocean depot play a larger role at decadal scales. So together, these results highlight a strong non-stationarity in the Tibetan Plateau hydrology and show that recent changes must be interpreted against the backdrop of very large natural variability, something that is crucial for future water management under climate change. Yes.
Right. I mean, it was very interesting analysis, and it's great to go back to 1200 period using the tree rings and then the gridded data on the Palmer Drought Severity Index from the tree ring data. And then you had, I guess, stream gauge data from the 60s, and then you were able to look at the relationship between the uh, droughts and wet cycles over centuries and compare that then with what we have seen from the instrumental record, the 5th to 95th percentile of stream flow. And I think one of your graphs in the paper was very striking in the showing that you had a lot of periods that were much drier than
Yeah.
what we have seen in the instrumental record, below the 5th percentile, and then some periods that exceeded the 95th percentile. And another plot in the paper that I found very interesting was the contrast in wet and dry periods. So when it's wet
Yeah.
in the north, dry in the south, and vice versa. And it's great that you were able to link it to history and the Ming Dynasty and their
Yeah.
fate. So it's really nice to be able to combine all sorts of data to increase our the reliability of your analysis and enforce what you are looking at. So I really enjoyed that paper. You and your team have done a lot of work, and there's a lot of discussion these days on the Mekong River and the term, I guess it's called the Lancang River in China,
Yeah.
looking at the relationship between climate, hydrology, and hydropower with the reservoirs along the Mekong. And maybe you can describe your analysis of the impact of those reservoirs and the different phases of reservoir development, filling stage, and then when the reservoirs are full, and then afterwards when they're operating the reservoirs, their impact on downstream water availability.
Okay, Bridge. I would like to start with briefly introducing the attributes of the Lancang Mekong River basins. So this river is one of Asia's most important transboundary river systems, and it originates on the Tibetan Plateau and flows through 6 countries before discharging into the South China Sea. The basin has extraordinary topographic gradient elevations dropped by more than 5 kilometers from source to mouth, and along the Chinese Reach, along the river, descends about 4.5 kilometers over roughly 20 to 100 kilometers. So this deep relief creates enormous hydropower potential, but also makes the system data poor and hydrologically complex. And in terms of the climate, the basin is dominated by the Indian monsoon and westerlies. Precipitation increases sharply from northwest to southeast, from about 700 to 800 millimeter per year in the upper Lancang to over 3,000 millimeter in parts of Laos and Cambodia. And in terms of the hydrological regime, it is strongly seasonal. Around 75 to 85% of annual runoff occurs during the wet season, from June to November, with peak flow typically in August or September. And in terms of the hydropower development, a cascade of large reservoirs has been constructed in the Lancang River in China, including Nozhadu with an installed capacity of about 5.9 gigawatt, Jinghong at 1.75 gigawatts. And so the Lancang mainstream contributes on the order of about 1% of China's total installed electricity capacity. And so the Lancang Mekong is a classical example where climate forcing, extreme topography, and large-scale hydropower regulation interact. Understanding this system requires separating natural monsoon-driven variability from human-induced flow regulation. And in terms of our study, we combine hydrological modeling and the tree ring reconstruction together with remote sensing data sets to try to understand the impacts of dams construction on the flow for 3 different periods. So we actually we explicitly separated the Lancang Mekong River's hydrology into three phases. The first is the pre-impact period, the transition period during dam construction and filling. This is the second stage. And the third phase is the post-impact operation period. Well, during the pre-impact period, from 1916 to 1991, the observed stream flow closely followed natural climate-driven variability. So using in situ data combined with our hydrological model, the QuestRS hydrological model, we reconstructed the natural runoff, which represents the response to climate law. And for the transition period from 1990 to 2009, it marks dam construction and reservoir filling. So during this period, we see the clearest negative impact on total stream flow, especially at upstream stations such as Chiang Saen in Thailand. And the reservoir filling reduced the annual discharge, creating a growing divergence between observed and natural runoff. And this reflects the water being temporarily stored to fill dead and active storage. And in the post-impact operational period, especially from 2010 to 2014 and after, the signal changes. And the total annual stream flow gradually returns toward nearly natural levels, indicating that the strongest impact occurs during filling rather than long-term observation. But the signal redistribution of flow is substantial. Reservoir operations reduce wet season flows and increase dry season flows. This has benefits: flood mitigation during the monsoon and dry alleviation in the dry season, which can be especially valuable during recent extreme droughts linked to anomalous monsoon. However, there are also negative consequences. One key concern is the sediment retention. Large reservoirs trap sediment that would otherwise nourish the Mekong floodplains and the delta. So reduced sediment delivery increases risks of delta subsidence, coastal erosion, and ecosystem degradation, particularly in Vietnam. So in summary, dam filling causes temporary reduction in total stream flow, and the dam operation stabilize annual volumes, but fundamentally alter seasonal timing. The system experiences clear trade-off: improved flood and drought regulation upstream, but growing downstream concerns related to sediment ecosystems and long-term delta sustainability.
Yeah, that's
Yeah.
fascinating and really nice that you disaggregated temporally then the construction and filling of the reservoirs and their impact on flow, and then you were able to compare with the pre-reservoir period to know what the natural system looked like, and then also quantified the impacts of dam operations then on downstream flow and providing more flow during droughts and retaining water during flood periods. So evening out the water supply, because you need to in order to support hydroelectricity, then you want a fairly uniform discharge. And that elevation difference along the Lancang Mekong River is amazing, and I guess the hydropower potential is huge, as you said, 1 to 5 gigawatts. So very, very nice study. I guess the last topic I would like to discuss a little bit, and we're running out of time, but is your work on the North China Plain. I mean, there's a lot of discussion on global hotspots of groundwater depletion in many regions. In the Upper Ganges, North China Plain was one of them. The parts of the High Plains upper in the U.S. and the California Central Valley. Um, but in China, then you have built the south to north water diversion system to transfer water from the Yangtze in the south, the humid south, to the North China Plain, which is a semi-arid region, to support municipalities. You have huge population density there in the North China Plain, and also a lot of agriculture. So would really appreciate if you can describe that a little bit for us, Dee.
Okay, so let me start with describing the geography and the climate for the North China Plain. So it is one of the world's most severe groundwater depletion hotspots, but it is also one of the cradles of Chinese agriculture. And this region is characterized by deep, fertile, and alluvial soils formed by long-term deposition from the high Yellow and the Huai rivers and their tributaries. So because of this exceptional soil fertility, the plant has been a core grain producing region since ancient times, supporting dense population and intensive farming well before modern irrigation existed. Well, so the fundamental challenge in today arises from a structural mismatch between climate and agriculture. About 60% of annual rainfall falls during the summer monsoon, while the dominant crop, winter wheat followed by summer maize, requires irrigation in the dry spring. For decades, this gap was filled almost entirely by groundwater pumping. Well, so the plain is bounded by the Taihang Mountain to the west and the Yan Mountains to the north, with rivers heavily dammed since the 1950s for flood control. As a result, surface water availability declined sharply, and cities like Beijing and much of the plain became overwhelmingly dependent on groundwater. Over the past 4 decades, groundwater levels fell by 20 to 60 meters, representing a cumulative deficit of roughly 180 cubic kilometers. So a turning point came with large-scale human intervention, especially the south to north water diversion project, the Central Road. Since 2014, water from the Dajiangkou reservoirs on the Han Yangtze system has been delivered along a 1,200 kilometer canal, supplying Beijing, Tianjin, and cities along the Taihang Piedmont. So between 2015 to 2024, this road alone delivered about 45 cubic kilometers of water, comparable to the long-term Yellow River imports. Well, so in terms of our study, by combining in situ ground depth measurements and grid satellites and the large-scale surface water and groundwater coupled modeling, and we found that the increased precipitation explains about 45% of recent recovery, and water diversion and ecological replenishment account for roughly 30%, and water conservation and demand management contribute the remaining 25%. And the results are striking. After decades of decline, groundwater storage shifted from losses of up to -2 to -5 cubic kilometers per year to a net gain of about 6.5 cubic kilometers per year after 2020. And the groundwater levels have been recovering at a rate of about 0.7 to 0.9 meters per year. So recovery is the strongest in urban areas like Beijing and mainly in shallow aquifers. That said, this recovery is managed, not free. The system comes with real energy and treatment costs. There are ongoing concerns about the ecological impacts, especially in the water source region, particularly the impacts of flow reduction on the lower reaches of the Han River. So the key lesson is not that diversion alone fixes the depletion, but that large-scale aquifer recovery is possible when climate variability, infrastructure, and governance are aligned through integrated water accounting. Yes.
So yeah, I mean it's amazing, a huge project, you know, with three separate routes, and you described the central route from the reservoir on the Yangtze to the North China Plain. And I recall visiting Shijiazhuang in the North China Plain many years ago, and you know, they were monitoring groundwater levels declining by a meter and a half per year. And
Yeah.
the winter wheat is when you really need all of that irrigation. And that's heavy reliance on groundwater and now bringing in surface water. And it's somewhat similar to what they've done in California with the State Water Project and the Central Valley Project, with the aqueducts taking water from the humid north to the Central Valley to support
Yeah.
irrigation there, and conjunctive management of surface water and groundwater. But I guess the difference is you have huge populations in Beijing and Tianjin, and most of the diverted water is going to those municipalities, but then that frees up water for agriculture. And so I really appreciate that you were able to disaggregate the impacts of climate variability and increased precipitation since 2020, and also conservation and other things, rather than just simply saying, well, they're diverting the water and the groundwater is recovering
Yes.
and that's
You're right.
it.
Yeah.
So it's
Yeah.
very important to link, you know, the policies and the infrastructure to the impacts, because it's occurring within a context of many other things with climate and other processes. So, Dee, I guess the last thing is, you know, your team, you've described a lot of applications of remote sensing and also instrumental data monitoring and modeling analysis, and I guess you're increasingly using artificial intelligence and machine learning. Maybe you can describe how you see the use of AI and ML, and how you see things going forward, how you will use AI and ML to improve your workflow.
Okay. Yeah. Thank you, Bridget. And in the remote sensing area, we have been facing a key challenge. That is the trade-off between the spatial and the temporal resolution provided by different satellite platforms. For example, NetSat provides long-term records but suffers from sparse temporal coverage and data gaps. And other sensors like MODIS offer higher revisit frequency but coarser resolution. So the trade-off has limited our ability to detect the seasonality, long-term trends, and extremes of the surface water bodies consistently at the global scale. So what we do is fuse multiple satellite datasets using the UNet model operating on both cloud platforms such as Google Earth Engine and supercomputers at our university. So to explore both spatial and temporal complementarity. So AI helps us optimize across sensors, constrain uncertainties, and generate ensemble consistent lake surface intent. So even under cloudy conditions or during rapid hydrological transitions. And based on the technological framework described above, we decompose lake dynamics into three distinct components: the long-term trends reflecting decadal expansion or shrinkage. The second is the interannual variability driven largely by wet-dry climate cycles. And the third is the seasonality, capture intra-annual transitions between inundation and desiccation. So what we found at the global scale, the seasonality dominates the lake surface dynamics. Salinity-dominated lakes account for about 2/3 of global lakes. And what we tested is based on the hydro basin lake datasets covering 1.4 million lakes globally. And approximately 60% of all lakes worldwide is also dominated by the seasonality. And slightly more than 93% of the population resides in basins with more than half of the lakes dominated by seasonality. So more broadly, this work shows how AI-powered remote sensing combined with big data and physical understanding allows us to move from static maps to dynamic process-oriented monitoring of inland waters at the planetary scale. That's essential if we want to understand how lakes respond to climate extremes and long-term change in the coming decades.
Right. So that's amazing, Dee. And I think NASA and other groups are using AI a lot to fuse data. And I guess we've always known some satellites have high temporal resolution but low spatial resolution, like MODIS, maybe 250 to 500 kilometers, and then high revisit times, high frequency revisits. But then Landsat maybe 30-meter spatial, but then every 15, 16 days revisit. So being able to fuse these different products then will help you to helps you to optimize spatial and temporal resolution and then address new issues. And your analysis of global reservoirs is really exciting. And also the different types of satellites. You mentioned cloud cover impacting optical satellites and then radar satellites not impacted. So the different types of data that we can combine together, and AI is really key to that. And I think in the past, maybe we spent half our time downloading data and then now being able to do it in Google Earth Engine, and avoiding that step. So it really is advancing a lot. So thank you so much for taking the time to describe your research today. Our guest today is Dee Long, who is a professor in hydrology and remote sensing at the Department of Hydraulic Engineering at Tsinghua University. And we look forward to seeing your future advances in hydrology, Dee, with your team. Thank you so much.
Thank you, Bridget, for your thoughtful guidance, and your suggestions are really helpful. Thank you, and looking forward to talking and collaborating with you.